All right, let's just jump right in. We spend so much of our lives online, right? We're sending everything from funny cat videos to our most sensitive private information flying across the internet. But have you ever stopped to think about how all of that stays, well, private? How do we keep our digital conversations from being read by literally anyone who might be listening in? I'm sure you've seen that little padlock and the letters HTTPS in your browser's address bar a million times. We're all told to look for it. That S, of course, stands for secure, and it's basically the digital bodyguard that protects you every single day. But what is it actually doing? Well, today, we're going to pull back the curtain and look at the incredible technology that makes all of our secure online communication possible. To really appreciate that little S, we have to understand what the internet is like without it. And here's the crazy part. The internet wasn't originally built with our security in mind at all, not even a little bit. It was designed to be wide open, kind of like a public postcard system, not a locked safe. This analogy just hits the nail on the head. Sending data across the early internet was exactly like mailing a postcard. Your message gets broken up into little digital packets, but those packets were sent completely out in the open. Anyone along the route, and I mean anyone, from someone at your internet provider to a hacker on the same coffee shop Wi-Fi, could just read the contents. Yeah, not exactly what you want for your credit card details, right? This digital eavesdropping has a name. It's called packet sniffing. An attacker can just sit back and listen to all the network traffic flowing by and read any data that isn't scrambled. Think of someone just standing by the world's mailboxes, reading all the postcards before they get delivered. It's a surprisingly simple, passive attack, but it's incredibly effective when there's no protection. But it gets scarier than just someone reading your mail. What if they could send you mail that looks like it's from someone you trust, like your bank? That's IP spoofing. An attacker can create a digital message, a packet, and just slap a fake return address on it. So a server might get this packet, think it's from a trusted source, and then carry out a malicious command. It's a classic case of digital impersonation. Okay, so we've established the internet is basically an open system, and that's a huge problem. So what's the solution? Well, we need to invent a secret language, a secret code that only the sender and the right receiver can understand, even if someone else is listening in. And this, my friends, is the art and science of cryptography. So there are two main ways to create the secret language. First, you have symmetric key cryptography. Think of it like a treasure chest with a single key that both locks and unlocks it. It's super fast, which is great, but it has one massive problem. How do you securely give the other person that one key to begin with? You can't just send it over the insecure internet. And this is where public key cryptography comes in and just brilliantly solves the problem. It uses two keys, a public key you can give to anyone, it only locks the box, and a private key that only you have, which is the only key that can unlock it. Now, this is why systems like RSA, a common public key system, are so powerful. Their security isn't based on some clever hiding spot. It's based on a really, really hard math problem. It's super easy to multiply two massive prime numbers together to get a new, even bigger number. That's kind of like your public key. But it is incredibly difficult, even for the world's best supercomputers, to take that final number and work backward to figure out the original two primes. And that difficulty, that's the rock-solid foundation of our online security. So having a secret language is awesome, but it only solves half the problem. We've protected our message from eavesdroppers, but what about those impersonators we talked about earlier? We need a way to prove that people and websites are who they say they are. This whole process is called authentication. This is the million-dollar question, isn't it? If you're about to encrypt a message with what you think is your bank's public key, you need to be 100% certain that you have the real key from your bank and not a fake one that an attacker gave you. So how do we solve that trust problem? The answer is a clever invention called a digital signature. You can literally think of it like an unforgeable wax seal on an old-timey letter. It proves two crucial things. First, that the message really came from the person who claims to have sent it, and second, that the message hasn't been messed with since it was sealed. It's a guarantee of authenticity. Exactly, authenticity and integrity. So here's how it works in a nutshell. The bank uses its private key to create a unique signature on a message. Then, anyone in the world can use the bank's public key to check that signature. It's a mathematical proof that only the true owner of that private key could have made it. And to tie it all together, we have trusted organizations called certificate authorities. They act like a digital DMV, issuing certificates that officially link a public key to a specific website, confirming that yes, this key really does belong to yourbank.com. All right, it's time to put all the pieces together. We have public key cryptography to share secrets, and we have digital signatures to prove identities. These two amazing concepts come together in a beautiful, rapid process that happens every single time you visit a secure website. It's called the TLS handshake. When your browser connects to a website, they do this super fast, three-step dance. First, the handshake itself. They say hello, the website shows your browser its certificate to prove it's legit, and they agree on what secret language they're going to use. Step 2 is key derivation. Now they use that secure public key magic to create a brand new single-use symmetric key. Why switch? Because symmetric keys are way, way faster for encrypting tons of data. And finally, step 3, data transfer. They use that new key to encrypt everything else for the rest of your visit. And just like that, in a fraction of a second, this whole process is complete. Your browser and the website have built a temporary, totally secure tunnel just for your conversation. It cleverly combines the best of both worlds, the unbreakable security of public key crypto to start things off, and the blazing speed of symmetric key crypto to do the heavy lifting. That entire elegant dance is the S in HTTPS. It's not just one thing, it's this whole amazing process. So that secure tunnel is incredibly powerful. But it's important to remember that it only protects your data while it's in transit, while it's flying across the internet. It's just one really important piece of a much, much larger security puzzle. You need what we call a layered defense. Beyond that tunnel, there's a whole ecosystem of other tools. For instance, firewalls act like the bouncers at a club, checking IDs at the door and blocking obviously bad traffic from ever getting in. Then you have things like intrusion detection systems. They're like the security cameras and guards already inside the club, constantly monitoring for any suspicious behavior. It's this combination of layers, all working together, that creates a truly strong defense. At the end of the day, online security isn't a problem that you solve just once and you're done. It's a constant race, a cat and mouse game between the people building the locks and the people trying to pick them. The really hard math that protects us today, like factoring those huge numbers, might one day be easy for powerful quantum computers. So the question we have to ask is this: what will the next generation of cryptography look like, and how will we have to adapt to keep our digital world safe for the future?